To stand before the gates of a Rusal smelter in the deep frozen heart of Siberia is to stand on the precipice of a terrestrial star, a place where the laws of thermodynamics are wrestled into submission by sheer brute industrial force. The wind here cuts through the thickest parka, carrying the biting chill of the taiga, a landscape of endless snow and pine that stretches for thousands of miles in every direction. Yet just beyond these concrete walls lies an environment so hostile, so intensely energetic, that it mimics the surface of the sun. This is not merely a factory, it is a cathedral of amperage, a monumental engine designed to rip the strongest chemical bonds in nature, apart using electricity generated by the crushing weight of immense rivers. The aluminum that frames your window, the casing of your phone, and the wings of the jetliners soaring overhead likely began their lives here, born from a violent electrochemical divorce inside a steel bathtub known as a reduction cell. We are about to enter a world where night and day are irrelevant concepts, replaced by the relentless thrumming rhythm of the potline, a beast that must be fed constantly, for if it is allowed to starve or freeze, the consequences are not just financial ruin, but the total, irreversible destruction of a billion-dollar infrastructure. The central conflict of this industrial titan is not market competition or labor shortages, but a battle against physics itself, specifically the terrifying threat of the frozen pot, a catastrophe that haunts every engineer and operator walking the floor. Aluminum smelting is a continuous process that operates at 960 degrees Celsius, a temperature maintained not by burning fuel, but by the resistance of the molten bath itself to the passage of massive electrical currents. If that power is cut, even for 4 or 5 hours, the bath begins to solidify, turning from a liquid conductor into a rock-hard, gray tomb that traps the valuable aluminum and destroys the intricate carbon lining of the cell. Once a pot freezes, it cannot simply be reheated. It must be jackhammered out, completely rebuilt, and restarted at a cost of hundreds of thousands of dollars per unit. And with hundreds of pots in a single line, a total power failure is a death sentence for the facility. This creates a perpetual state of high-stakes vigilance, a tension that hums in the air alongside the magnetic fields, creating an atmosphere where relaxation is a dangerous luxury. If detailed technical breakdowns of heavy industrial engineering and extreme manufacturing interest you, subscribe. I have got more of these coming. The scale of a facility like the Taishe or Boguchansky smelter is difficult to comprehend without visualizing the raw geography that necessitates its existence. These plants are located in the desolate expanses of Siberia, not because the weather is favorable or the labor is abundant, but because aluminum production is, in essence, the business of solidifying electricity. To produce a single kilogram of aluminum requires roughly 14 kilowatt-hours of electricity, enough energy to run an average American home for half a day, compressed into a block of metal the size of a book. Therefore, these smelters are tethered like hungry leviathans to the massive hydroelectric dams on the Angara and Yenisei rivers, consuming power on a scale that rivals entire nations. We are talking about gigawatts of power funneled through transmission lines that crackle and hiss, stepping down voltage but ramping up amperage to levels that seem fictitious to a standard electrician. Before we descend into the technical abyss of the electrolysis process, pause for a moment to absorb the sensory reality of the Potroom approach. The air outside is crisp, smelling of ozone and snow, with a silence so profound it rings in your ears, broken only by the distant rhythmic clanking of rail cars shunting raw materials. As you step through the heavy industrial doors, the silence is instantly annihilated by a low-frequency roar, a sound that is less heard and more felt, vibrating through the soles of your safety boots and rattling the fillings in your teeth. The temperature jumps 40 degrees in a single step, and the smell of pine is replaced by the acrid metallic tang of hot carbon, fluoride salts, and the distinct dusty dryness of alumina powder. This is the breathing room of the giant, the inhospitable transition zone, where the human body realizes it has entered a domain built for machines, not flesh. To understand the mechanics of this beast, we must first look at the raw material, a white powdery substance called alumina, or aluminum oxide, which arrives by the trainload in covered hopper cars. Alumina is the result of the Bayer process, where reddish bauxite ore is refined, but here at the smelter, the goal is to tear the oxygen away from the aluminum, a bond so strong that for centuries, aluminum was considered more precious than gold because no one could figure out how to separate it economically. The solution, discovered independently by Charles Martin Hall and Paul Héroult in the late 19th century, relies on a unique solvent called cryolite, a sodium aluminum fluoride compound that looks like crushed ice but acts like a magical key. Pure alumina melts at over 2,000 degrees Celsius, a temperature that would melt the containment vessels themselves, but when mixed with molten cryolite, the melting point drops to a manageable 960 degrees Celsius, creating a conductive bath or electrolyte in which the magic can happen. Imagine a kitchen experiment, but scaled up to the size of a football stadium and heated to the temperature of magma. If you were to dump table salt on a block of ice, the ice melts because the salt lowers the freezing point of water. Similarly, the cryolite flux dissolves the alumina, creating a soup of charged ions waiting for a command. That command comes in the form of direct current electricity, delivered at an amperage so staggering, often exceeding 300,000 amperes, that it creates a magnetic field strong enough to wrench a wrench from a mechanic's grip, if they are not careful. This current enters the pot through the anode, a massive block of carbon suspended from above, travels through the molten cryolite bath where it rips the oxygen atoms from the alumina and exits through the cathode, the carbon lining at the bottom of the pot. The sheer violence of this chemical reaction is hidden beneath a deceptively calm surface, a crust of solidified chemicals that traps the heat and gases inside the pot. Underneath this crust, the oxygen ions migrate to the carbon anode and react with it, essentially burning the carbon to produce carbon dioxide, which bubbles away while the aluminum ions drift downward, pooling as a layer of molten metal at the bottom of the crucible. It is a continuous consumption of carbon and electricity to birth pure metal, a process that requires the anodes to be replaced regularly as they are eaten away by the oxygen. Visualize a candle burning down, but instead of wax, the fuel is a distinct block of baked carbon weighing over a ton, and instead of a flame, the reaction is a silent, searing electrolysis that transforms white powder into silver liquid. Now step back from the chemistry and feel the atmosphere of the potline floor, a cavernous hall that stretches for a kilometer or more, filled with hundreds of these reduction cells arranged in long, precise rows. The perspective here is dizzying, a vanishing point of steel and concrete that seems to go on forever, illuminated by the harsh glare of sodium lights and the occasional hellish orange glow of an open pot. The heat is a physical weight pressing against your chest, and the magnetic field is a constant, invisible tide that pulls at every ferrous object on your person, a ghostly reminder of the rivers of invisible force flowing just inches beneath the floor plates. It is a place of solitude despite the noise, where workers move like astronauts in their protective gear, isolated by the need for respirators and earplugs, communicating in hand signals and intense stares. The machinery required to service these pots is as specialized as a spacecraft and as rugged as a tank, dominated by the pot tending machine, or PTM, a massive overhead crane that rumbles along rails in the ceiling. This machine is the nursemaid to the dangerous infants below. It carries fresh anodes, breaks the hard crust of the bath, and scoops out the molten metal, all while the operator sits in a shielded cab suspended above the inferno. When the PTM approaches a pot to change an anode, the scene turns cinematic. The crust breaker, a pneumatic chisel the size of a jackhammer, descends and smashes through the solidified top layer, sending chunks of hot crust splashing into the molten orange bath below. The old eroded anode, glowing cherry red and dripping with liquid salts, is hoisted into the air, radiating so much heat that you can feel your skin tighten from 20 meters away before a fresh black carbon block is lowered into place with surgical precision. This operation, known as anode setting, is critical because the positioning of the anode determines the efficiency of the cell. Place it too low, and it short circuits against the molten aluminum pad, causing voltage instability. Place it too high, and the resistance increases, wasting electricity as excess heat. The distance between the anode and the cathode, the anode-cathode distance, is often only 4 or 5 centimeters, a razor-thin margin of error maintained amidst splashing liquid metal and blinding heat. The computer systems that monitor these distances make adjustments of less than a millimeter, constantly tweaking the height of the massive carbon blocks to maintain the perfect electrical sweet spot. It is a delicate ballet performed by lumbering giants, where a single miscalculation can send the pot into an anode effect, a sudden spike in voltage that causes the bath to boil violently and release perfluorocarbons, potent greenhouse gases that the industry struggles to contain. Take a moment to breathe here, to let the image of the glowing anode fade and replace it with the sensory experience of the walkway between the pots. The floor grates vibrate with a specific frequency, a 60 Hz shudder that travels up your legs and settles in your spine, a constant reminder of the alternating current being rectified nearby. The air tastes different here, thick and dry, and despite the massive ventilation systems sucking fumes into the ceiling scrubbers, there is always a faint, lingering scent of sulfur and hot tar. A worker sits on a bench in a designated cool zone, wiping sweat from a face lined with coal dust, taking a long pull from a water bottle that has gone warm in minutes. The exhaustion here is not just physical, but thermal, a deep-seated fatigue that comes from the body fighting to cool itself in an environment designed to melt rock. The electrical infrastructure required to feed a pot line is a marvel of engineering in its own right, originating at the switchyard where high-voltage transmission lines from the hydroelectric dam terminate. Here, huge transformers step the voltage down from hundreds of thousands of volts to a more manageable level. But the real magic happens in the rectifier station. Pot lines run on direct current, or DC, because alternating current would simply vibrate the ions back and forth without separating them. Therefore, banks of massive silicon rectifiers act as electrical check valves, forcing the current to flow in a single direction. The bus bars, the conductors that carry this current, are not wires but solid slabs of aluminum the size of dining tables, bolted together in stacks that wind their way through the plant like the arteries of a titan. These bus bars are uninsulated because the voltage is relatively low, often less than 1,000 volts for the whole line. But the amperage is the killer, creating a magnetic field so intense that it creates a motor effect in the molten metal within the pots. The liquid aluminum and electrolyte actually swirl and wave under the influence of the magnetic forces, a hydrodynamic instability that engineers must carefully model and counteract. If the metal surface waves too much, it can touch the anode, causing a short circuit. To prevent this, the bus bars are routed in complex, computer-designed geometries to cancel out magnetic interference, effectively using the magnetic fields to pin the metal down and keep it flat. It is invisible sculpting, using the forces of electromagnetism to flatten a liquid mirror of molten aluminum hidden beneath a crust of salt. The production of the anodes themselves is a factory within a factory, a dirty, gritty process that contrasts sharply with the high-tech precision of the control room. The carbon plant takes petroleum coke, a byproduct of oil refining, and mixes it with coal tar pitch to form a hot, sticky paste that is vibrated and pressed into massive blocks. These green anodes are soft and non-conductive, so they must be baked in colossal gas-fired ring furnaces for weeks, slowly heating up to 1,200 degrees Celsius to carbonize the pitch and fuse the structure into a solid, conductive brick. The result is a dense black monolith that rings like a bell when struck, ready to be sacrificed in the electrolytic cells. There is a distinct visceral difference between the carbon plant and the electrolysis pot line. The carbon plant is a place of black dust, crushing gears, and the heavy smell of hydrocarbons, reminiscent of a 19th century coal mine. Everything is coated in a fine layer of black powder that turns into a slick grease when mixed with sweat. And the machinery here, crushers, screens, mixers, operates with a brute, mechanical violence. In contrast, the pot line is a place of electrical silence and thermal intensity, where the violence is atomic rather than mechanical. Transitioning between these two zones feels like moving from the engine room of a steamship to the core of a nuclear reactor, a shift from the physical grinding of matter to the silent manipulation of energy. Once the aluminum has pooled at the bottom of the pot, it must be harvested, a process known as tapping. A specialized vehicle, often looking like a cross between a forklift and a vacuum truck, drives up to the pot, inserts a steel siphon tube through the crust, and uses suction to draw the molten metal into a heavily insulated crucible. This is a moment of extreme danger. The liquid aluminum is at 960 degrees Celsius, and it looks exactly like water, with no visible glow and bright light to warn of its temperature. If a single drop of water were to find its way into that crucible, perhaps from a leak in the roof or condensation on a cold tool, it would instantly flash into steam, expanding 1,600 times in volume and causing a steam explosion that sprays molten metal like shrapnel. The crucible, now filled with several tons of liquid metal, is transported to the cast house, the third major component of the smelter complex. Here, the raw aluminum is poured into holding furnaces where it can be alloyed with small amounts of magnesium, silicon, or manganese to give it specific properties: strength for construction, flexibility for foil, or heat resistance for engine blocks. The atmosphere in the cast house is different again. It is cleaner, brighter, but filled with the perilous beauty of flowing metal. Operators in silverized suits oversee the transfer of the liquid into launders, ceramic-lined troughs that channel the glowing stream into casting pits, where it is solidified into ingots, billets, or slabs. Knowing what you now know about its real-world production bottlenecks and extreme hazards, do you think the massive capital investment in this facility was worth it? Share your thoughts below. The casting process itself is a battle against impurities. As the metal flows, it passes through ceramic foam filters to catch any microscopic inclusions of bath or oxide that could weaken the final product. Even dissolved hydrogen gas, which can cause porosity and bubbles in the solid metal, is removed by spinning rotors that inject inert argon gas into the melt, gathering the hydrogen like a sponge. Finally, the metal enters the water-cooled molds of the direct chill casting machine. As the bottom of the mold slowly descends, jets of water freeze the aluminum shell, allowing the solid ingot to emerge continuously from the bottom, a gleaming silver monolith rising from a pool of fire. Let the roar of the furnaces fade for a moment and consider the silent, invisible network that keeps this entire operation from collapsing: the logistics of raw materials. For every ton of aluminum produced, the plant needs 2 tons of alumina, half a ton of carbon anodes, and significant amounts of fluoride salts. This means a constant, never-ending train of rail cars arriving from the coast, bringing alumina that may have originated from bauxite mines in Guinea, Australia, or Jamaica. The supply chain is a global conveyor belt that stretches across oceans and continents, terminating in this frozen Siberian outpost. If a storm in the Atlantic delays a shipment or a rail strike in Russia halts the trains, the buffer stockpiles at the smelter begin to dwindle, and the clock starts ticking toward the nightmare of a shutdown. This dependency on logistics highlights the fragility of the massive industrial organism. It is a beast that eats continuously and cannot hunt for itself. The silos that tower over the plant, filled with white alumina powder, are the stomach of the facility, and their levels are watched with obsessive attention. Inside the silos, the powder behaves like a fluid, aerated by air jets to keep it flowing, cascading down through air slides, pneumatic conveyors that float the powder on a cushion of air directly to the pot hoppers. It is a silent, pneumatic circulatory system that ensures every pot gets its dose of ore exactly when it needs it, controlled by automation systems that track consumption to the gram. The environmental reality of such a facility is the elephant in the room, a legacy of heavy industry that modern engineering fights to mitigate. In the past, aluminum smelters were notorious for emitting fluoride gases that would strip the leaves off trees and etch the glass of nearby windows, but modern plants like Taishe use massive dry scrubber systems. These are essentially giant filters where the exhaust gas from the pots is passed through fresh alumina powder before it even enters the pot. The alumina absorbs the fluorides, trapping them, and is then fed into the pot, returning the valuable fluoride to the process. It is a closed loop of recycling that captures over 99% of the harmful gases, transforming a pollution problem into an efficiency solution. Stand now on the catwalk overlooking the gas treatment center, a labyrinth of massive ducts and silos that dwarfs the human form. The sound here is the rush of wind, millions of cubic meters of air being sucked from the pot rooms, scrubbed, and released. It is a testament to the sheer volume of gas involved. The fans are the size of jet engines, driven by motors that could power a small ship. Despite this technology, the air around the plant still carries the faint, unmistakable signature of industry, a reminder that while we can minimize the footprint of such massive energy conversion, we cannot eliminate it entirely. The snow outside the plant walls, while white, often bears the microscopic traces of the struggle occurring inside, a chemical signature written on the landscape. The human element of the smelter is perhaps the most compelling story of all. The workforce here is a mix of generations, from gray-bearded veterans who remember the Soviet era to young engineers fluent in digital automation. They work a swing shift schedule that rotates through days, nights, and weekends, disrupting circadian rhythms and creating a unique subculture of people who live while the rest of the world sleeps. In the break rooms, the talk is of amperage efficiency, anode quality, and the temperature of the bath, a specialized language that isolates them from the general population. They are the keepers of the flame, the guardians of the pots, bound together by the shared knowledge that a mistake by one can endanger them all. Consider the potroom superintendent, the captain of this landlocked ship whose phone is never turned off. Their mind is constantly modeling the thermal state of the pot line, balancing the heat input from the electricity against the heat loss through the walls of the pots. In winter, when the ambient temperature drops to -40, the pots lose heat faster, requiring adjustments to the voltage or the insulation. In summer, the opposite problem arises. It is a constant game of thermal chess played against the seasons, where the pieces are 1,000-degree crucibles and the board is the Siberian tundra. The maintenance crews are the unsung heroes who keep the mechanical heart beating. They repair the crust breakers, reline the ladles, and service the massive cranes. Working on a PTM crane is a job for the fearless. Suspended 20 meters above the pot line, exposed to the rising heat and fumes, they change hydraulic hoses and swap out electrical contactors. The dust is conductive, so electrical panels must be sealed and pressurized with clean air to prevent short circuits. Every tool they use is tethered to prevent it from falling into a pot below, which would not only destroy the tool but contaminate the aluminum with iron, ruining the batch. Transition your focus to the reline shop, the place where old pots go to be reborn. A reduction cell has a lifespan of about 5 to 7 years before the carbon lining fails or the steel shell deforms. When a pot is taken out of service, it is allowed to cool. a process that takes days before being demolished. The spent pot lining, infiltrated with fluorides and cyanides, is a hazardous waste that requires careful handling and treatment. The rebuilding process is meticulous. Layers of insulating brick, barrier materials, and finally, the cathode blocks are installed with the precision of a bricklayer building a fireplace for a king. The seams between the blocks are rammed with a hot carbon paste, and the whole structure is baked to form a seamless, liquid-tight vessel. This cycle of birth, death, and rebirth of the pots is a slow rhythm that underpins the faster rhythm of the daily production. A smelter is never finished. It is always in a state of partial renewal, with some pots being started up, others running at peak efficiency, and some nearing the end of their lives. Starting a new pot is a delicate operation called bake-out, where the lining is heated up using gas burners or electrical resistors before the molten bath is poured in. If heated too fast, the lining cracks, too slow, and production is lost. It takes weeks for a new pot to reach thermal equilibrium, a period of intense monitoring where the pot is treated like a patient in intensive care. The economic model of the smelter relies on the concept of value-added production. Selling raw aluminum ingots is profitable, but the real money lies in specialized alloys. The cast house is therefore a laboratory as much as a factory where metallurgists tweak the recipes to create alloys that are lighter, stronger, or more corrosion-resistant. A billet of 6061 alloy, destined to become a bicycle frame or a structural component, must meet strict specifications for grain size and chemical composition. The samples are cut, polished, and analyzed in spectrometers that scream out the elemental breakdown in seconds, ensuring that the customer gets exactly what they paid for. Imagine the journey of a single aluminum atom in this facility. It arrives bonded to oxygen in a grain of white powder, travels thousands of miles by rail, gets blown through a pipe into a silo, and then drops into a boiling bath of fluoride salts. There, it is ripped from its oxygen partner by a bolt of electricity, drifts down through the molten chaos, and pools with billions of its kin. It is sucked up into a crucible, alloyed with magnesium, filtered, and frozen into a solid log. Finally, it is loaded onto a train, leaving the frozen wasteland of Siberia to be extruded, machined, and assembled into a product that might end up in your pocket or your driveway. It is a journey of transformation, driven by energy and directed by human will. The future of these smelters lies in the quest for the inert anode, the holy grail of the aluminum industry. Currently, the carbon anode is consumed, producing carbon dioxide. For every ton of aluminum, roughly 1.5 tons of CO2 are released from the anode reaction alone. Rusal and other giants are racing to develop anodes made of advanced ceramics or metal alloys that conduct electricity but do not react with oxygen. If successful, the byproduct of smelting would be pure oxygen instead of CO2, effectively turning the smelter into a massive oxygen generator. This technology, currently in pilot stages, represents the next great leap, a shift as significant as the original discovery by All and Eruld. Yet, until that day comes, the carbon anodes continue to burn, and the trains continue to roll. The sheer momentum of the facility is its defining characteristic. It is a machine that cannot stop, a system designed for continuous, relentless throughput. To walk the floor of a Rusal smelter is to witness the industrial era in its most raw and powerful form, a place where the delicate balance of nature is suspended in favor of the rigid laws of metallurgy. It is a place of terrible beauty, where the danger is palpable and the engineering is sublime. As we step back out into the Siberian cold, leaving the roar and the heat behind, the silence of the taiga reclaims the senses. The plant stands as a glowing island in a sea of darkness, a monument to the ability of humanity to harness the fundamental forces of the universe. It is a reminder that the comforts of modern life are forged in places of extremity by people who work on the edge of the habitable world, managing forces that would destroy them in an instant if respect were lost. The aluminum in your hand carries the invisible memory of this place, of the magnetic hum, the fluoride smell, and the frozen landscape that surrounds the fire. The legacy of the Hall-Héroult process, executed at this massive scale, is a testament to the brute force approach to chemistry. We do not coax the metal out of the ore, we blast it out with the energy equivalent of a thunderstorm. It is an inefficient, messy, dangerous, and magnificent way to build the world, a method that has remained largely unchanged in principle for over a century, even as the computers controlling it have become infinitely more complex. The interplay between the digital brain and the analog muscle of the plant is where the modern story lies, in the incremental gains of efficiency clawed back from the chaos of the potline. Ultimately, the smelter is a reflection of civilization's hunger for material. We built these cathedrals of current because we need the metal they bleed. We endure the pollution and the danger because the alternative is a world without flight, without modern construction, without the lightweight connectivity that defines our era. The workers who tend the pots are the stokers of the modern engine, keeping the fires burning in the dark, ensuring that the flow of silver metal never ceases. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.